Hello, students. Welcome to Semester 4. I am Mr. Satish Sheshkar, and today we are beginning Unit 1 of Refrigeration and Air Conditioning. We must start with a strict technical definition. Refrigeration is the engineered, controlled extraction of heat from a target space. The specific goal is to maintain that space at a temperature below the ambient environment. This is distinctly different from air conditioning. Air conditioning requires the simultaneous control of 4 factors: temperature, humidity, air purity, and the proper distribution of that air. Refrigeration deals solely with heat removal. Before you can design complex human comfort systems or calculate loads for food preservation logistics, you need to understand exactly how heat behaves when we force it out of an environment. Therefore, before analyzing modern mechanical AC systems, engineers must first master the fundamental physics of simple heat removal, basic refrigeration. To study this, we divide refrigeration systems into 2 primary categories: cyclic and non-cyclic methods. Non-cyclic systems do not use mechanical compressors or continuous loops of refrigerant. Instead, they rely on single-use physical state changes, where a substance naturally absorbs heat as it changes its form. Your syllabus covers 4 specific non-cyclic architectures. We will examine ice refrigeration, dry ice, evaporative refrigeration, and steam jet refrigeration. All 4 of these methods rely on a single thermodynamic mechanism. They exploit phase changes to act as a one-way thermal sink. We begin with ice refrigeration. For this to work, we absolutely require a heavily insulated chamber. If the chamber is not insulated, ambient heat from the outside air will infiltrate the system and waste our cooling capacity. Look at this diagram of an insulated cooling chamber. This illustrates the latent heat of fusion. Solid ice absorbs thermal energy directly from the surrounding food. It uses this energy to break its molecular bonds, turning from a solid into liquid water. If a specific application requires lower temperatures than ordinary ice can provide, engineers introduce an ice-salt mixture. The salt chemically depresses the freezing point, allowing the system to achieve lower cooling temperatures inside the chamber. Now, let us apply this phase change concept to a liquid. This brings us to evaporative refrigeration, which relies on the latent heat of vaporization. This cross-section of an earthen clay pot shows the process clearly. Liquid water seeps through the porous clay walls to the exterior. As ambient heat hits the surface, that water turns into vapor, carrying thermal energy away from the pot. The escaping vapor is composed of the highest energy molecules. When they leave, the liquid that remains behind has a much lower average kinetic energy, which means the remaining water is successfully chilled. Think about this in your daily life. Why does spirit or hand sanitizer feel drastically colder on your palm than regular water? It evaporates faster because it has a lower boiling point, pulling latent heat directly off your skin. Whether an engineer uses melting ice or evaporating water, the phase change of a medium actively steals kinetic energy from its immediate surroundings, creating a passive but powerful cooling mechanism. Let us advance to our third method.
Dry ice is explicitly the solid state of carbon dioxide. It is not frozen water. It cools through a thermodynamic process called sublimation. As you can see, the solid transitions directly into a gas without ever entering a liquid phase. For mechanical engineers, dry ice provides a critical specification. During sublimation, it maintains a steady, extreme temperature of -78 degrees Celsius. Because of this low temperature and the lack of moisture, it is heavily used in aircraft cargo transportation and critical frozen food logistics, where liquid water runoff would damage the packaging or the product itself. Bypassing the liquid state entirely provides extreme low temperature stability with zero moisture residue. This makes sublimation the premier non-cyclic choice for high-stakes transport. Our final method presents an interesting engineering paradox. How can we freeze water by forcing it to boil? Look at this pressure-temperature graph. A fluid's boiling point is proportional to ambient pressure. Dropping pressure drops the boiling temperature. By reducing pressure to create a vacuum, we lower vaporization temperature. We achieve this mechanically using a steam jet system. High-velocity steam is forced through a converging-diverging nozzle. Based on Bernoulli's principle, extreme velocity induces a severe pressure drop.
This creates a vacuum that aggressively pulls vapor up and out of the connected flash chamber below. To replace the vapor that is constantly being extracted, the liquid water remaining in the flash chamber begins to boil at a low ambient temperature. To do this, the water must draw the required latent heat from its own mass. By engineering a severe fluid pressure drop, we mechanically force a phase change to occur at ambient temperatures. We utilize pure fluid dynamics and thermodynamics to chill a system, entirely without chemical refrigerants. This matrix categorizes the 4 methods we have covered by their specific phase change mechanisms. We have ice, utilizing fusion; evaporative, using vaporization; dry ice, operating on sublimation; and steam jet, utilizing pressure-induced vaporization. Despite their varying architectures, all 4 systems share the exact same underlying principle. They utilize the physics of latent heat to extract thermal energy. However, they also share a critical limitation. Eventually, the non-cyclic system runs out of its cooling medium. The ice completely melts, the water entirely evaporates, and the dry ice vanishes. While highly effective for specific closed-duration tasks, non-cyclic systems cannot provide the infinite, continuous cooling required for large-scale modern applications. To solve this limitation, to achieve continuous cooling without running out of a medium, engineers developed cyclic mechanical refrigeration, which we will explore in our next lecture. Take a moment to review your notes. If you have any questions regarding phase changes or latent heat, please discuss them in the classroom now. Thank you for your attention today. On behalf of myself, Mr. Satish Sheshkar, and the university. Remember, mastering these basic thermal sinks is the absolute prerequisite for understanding the complex mechanical cycles you will face in your upcoming RGPV diploma examinations. Good luck and keep studying.